Hello and welcome to this, well, for want of a better phrase, audio series, I guess, which we've decided to call Driving Sustainability, the Role of Steel in the Automotive Industry. So there's a good pun there as well. I must warn you, it does get a bit technical, but hopefully there's some light-hearted conversation as well between me and Brian that you might enjoy. In this first episode, called The Carbon Footprint of Steel in Electric Cars, we're going to try and get an appreciation of the carbon footprint of the steelmaking industry for automotive applications, along with discussing the steel grades typically used in this industry. So, if you're an environmentalist or metallurgist, then you're going to love this podcast. Let's get started on this. Hello, I'm Michael Shakib, and joining me here is Bryan Jones. Say hello, Brian.
Hello.
Brian and I both work for Swansea University in the role of industrial lecturers. Over the years, I've developed courses on things like practical metallurgy, energy and power, tin plating, semiconductor manufacturing, and other courses which tend to serve the industry around us in South Wales. Brian, who's got many years' experience in the steel industry, has developed and given courses on things like introduction to materials, manufacturing technology, coke making, steel making, meeting customer expectations. That was one, Brian, wasn't it?
Yes.
Yeah, joining technology and a lot more other things as well. What we could say here, though, is that we both, or Brian especially, knows a little bit about making steel, which is quite pertinent to this. However, things have changed in the recent years, and there's a greater focus on subjects relating to climate change, net zero, and so on, which has meant us both sort of re-educating ourselves. Would you say that, Brian?
Yeah, definitely, yes.
Yeah. I've written a course on circular economy, critical raw materials, renewable energy. I'm in the middle of writing a course on project finance for renewable energy projects, which might seem a bit strange, yet I can assure you it's not that strange when you look into it. Brian has produced some new courses on the hydrogen economy, sustainability in the transport and mobility sector, and he's currently working on a carbon accounting course, aren't you, Brian?
Yes, that's right, yes.
Yeah. But what we're here to talk about today is something different to all that. It's electric vehicles. And it sort of brings together our knowledge of the past, shall we say, in steel making and these net zero subjects. Okay, we do actually have a full course written on EVs by an ex-colleague of ours, Tom Taylor, who I believe has left us for Red Bull Racing. Did he leave us for Red Bull Racing?
Yes, he did, yes.
He did, yeah. Oh, how dare he. He also wrote a course on fossil-free steels, which we're going to talk about later, and we're going to talk about that because actually it's all connected together. Brian and I, we're not vehicle experts, we're not engine mechanics, we're not aerodynamicists, we're not car designers. We don't actually know a lot about vehicles in general. However, we do know a little bit about steel, well enough to talk about here. And why is that important? Well, it's no secret. Steel is the main material which is being used in the manufacture of cars and EVs.
Yeah, and is likely to be in the future as well.
Well, that's it. So we'll read, what did Elon Musk say? He said that there's no holding back on the production of steel for EVs going into the future, and steel in general for that matter. He didn't say that. Brian said that. Regardless of the threat of aluminium, 99% of cars are still made from steel. And why is this even a talking point? Well, I remember earlier when I said Tom has written a course on fossil-free steels. That's important because the production of steel produces high levels of CO2, and that's causing a bit of an issue, isn't it? I could stop there and carry on talking about electric cars, but I want to go on a little bit further to frame the subject of this. I don't know what you call this, presentation, podcast, chat, whatever. So the carbon footprint of steel, it can be argued, and me and Brian have argued this morning, not argued, discussed rather, about what the numbers really are. But let's just say the carbon footprint of steel is about 1.4 tonnes per tonne of strip steel produced. Strip steel being quite the operative word there, isn't it?
It is, yes.
Steel comes in
strip steels are used in the automotive industry for the construction of the body in white.
And we'll talk about that later, won't we, when it comes to talking about how cars are made.
Yes.
So those figures are according to the IEA, And the McKinsey, and this that was 1.4 tonnes and 1.85 tonnes, according to the McKinsey and World Steels Association. We'll talk about this a little bit more. These figures come from making steel by means of using the traditional blast furnace and basic oxygen steel making route, and the electric arc furnace route, which uses recycled steel as opposed to the blast furnace method. These numbers we've just talked about are the weighted average of both these methods, but to give some comparative figures, the CO2 footprint of the blast furnace method is about 1.8, and the electric arc furnace method about 0.3 tonnes of CO2 produced per tonne of steel. So basically what we're saying here is we've got two different methods of producing steel, and you're going to later tell us of a hybrid sort of third method, something that links into the electric arc furnace.
Yes.
But we can save CO2 by using the electric arc furnace method. Now, why is that important, Brian, in relation to what's happening down the road from us right now?
Well, if we're to reach net zero carbon emissions by 2050, then there has to be a significant reduction in carbon dioxide emissions from steel production. And the major driver for the use of the electric arc furnace is because the level of emissions are significantly lower than via the blast furnace Boss steelmaking route. So we see this gradual increase worldwide in the production of steel by electric arc furnace route. However, there are major challenges associated with electric arc furnace in producing the specialist grades of steel that are required, for example, in automotive and packaging applications. So we'll cover that topic during this discussion.
Brilliant. Nice introduction there, Brian. So Tata Steel down the road, they've been saying this for years, haven't they?
Yes.
But we're getting a little bit closer now, aren't we, to them changing over their processes. That's
right. I mean, the intention at Port Talbot is to close down the blast furnaces and the Boss steelmaking route and to replace that mode of steelmaking with an electric arc furnace.
Okay. This is a big project. Okay, so we know that we've got certain ways of producing steel, and we know that they both produce CO2, one more than the other. This leads us then to ask some obvious questions in relation to car manufacturing, such as how much CO2 is produced for the making of EVs, what's the embodied energy of these cars, and so on and so forth. These kind of questions, which we probably won't be able to answer ourselves, but we might get a little bit close to appreciating the answer.
Yeah.
So, but before going on to the discussion that Brian was just alluding to there, I'd like to read out an executive summary from a 2021 American Iron and Steel Institute report, and it's called Steel Industry Role in the Future of Electrified Vehicles. And there is a reason why I want to do this, and it might seem tedious, but it does bring into something the next subject we're going to talk about, which is steel grades. So here we go. As manufacturing industries continue to look at ways to respond to climate change, automakers in the US and around the world have taken the lead by implementing vehicle electrification strategies to achieve substantial CO2 emission reductions. The American Steel Institute plays a critical role in achieving those reductions. Automakers are ramping up production of mild hybrid, plug-in hybrid and battery electric vehicles, which they've called here BEV. I'm just going to call them EVs from now on because it's easier, as an integral part of their product portfolios. The focus on these platforms suggests a deliberate and systematic migration towards product portfolios dominated by EVs in an effort to become carbon neutral within the next 2 or 3 decades. This migration is also being reinforced by governments worldwide, which are either providing incentives for EV use or mandating their use in the near future. Automakers are now competing to develop affordable EVs that offer drivers an acceptable travel range without compromising the functionality and features available to them in current internal combustion engines, ICE, vehicles. An increase in EV range is sensitive to both onboard battery capacity and vehicle efficiency, including mass, which is probably pertinent to our conversation, I would say, more than anything. As battery technologies continue to evolve over the next decade, their energy density will increase, while their costs are expected to decrease. We can hope. Consequently, that was me interjecting there. That's not written in the report. Consequently, automakers are expected to develop cost-effective, lightweight steel EV architectures. I suppose we will talk about what is meant by architectures, will we, Brian?
Yes, well.
Yeah. Using a broad spectrum of steel grades available. Instead of using higher cost alternatives such as aluminium, magnesium and composites, which have their place, have been tried out. But I think Brian will talk a little bit about the different Tesla models that have come out recently, made out of aluminium and steel, as a little anecdote. Okay, so cost savings achieved from using steel can be leveraged to maximise the onboard battery capacity. Meanwhile, increased proliferation of EVs will be accompanied by additional crash requirements, which is really important, over and above existing standards to minimise intrusion into the battery pack, maintain pack structural integrity, and ensure occupant safety, which are, really, really important things. These requirements are expected to make steel the material of choice for future EV designs worldwide. Well, why have I read this out? It's because this introduces another consideration. Steel is not one product. Steel comes in thousands of different variations, and we call these variations grades. These will all have varying properties, chemistries, complexities during the manufacturing process, and hence they'll all have different prices as well. I suppose the question is here today is, can we make the same grades with both of our processes that we have discussed previously? That's the big question that hopefully Brian will be able to answer today. What this highlights to me is that steel is not so simple, and we don't need to go down the road of talking about battery technology to have a long discussion on electric cars, do we, Brian?
No, definitely not.
We know there's two main methods of producing steel. We know there's thousands of grades of steel, and we also know not all of them are actually suitable for the automotive industry. So we're talking about a limited sort of range of materials that are needed for the automotive industry.
Yeah.
And my question then, Brian, to start off, and this is what we intend to cover here, is could you give us like an overview of the use of steels for the automotive application, for automotive applications? How do we make them? How do we use them?
Right. Up until the 1950s, uncoated mild steel was the primary product used in automotive construction worldwide. However, since then, there's been an increasing focus on reducing the mass of vehicles because of concerns with respect to exhaust emissions. So the steel industry now has played a leading role in developing grades of steel of higher strength so that thinner steels can be used to replace the mild steel that was used traditionally as a way of reducing the mass of the vehicle and therefore the harmful emissions generated.
Thanks for that, Brian. So my next question to you then is, what do you mean by mild steel? You mentioned mild steel. What do you mean by that?
Mild steel is a low strength product with excellent levels of formability that can be used in all sections of a vehicle architecture. However, there is because of the need to reduce vehicle weight, a whole generation of high strength steels initially were developed in the 1950s and 1960s to replace mild steel in areas where the formability wasn't a significant issue. So high strength steels offered benefits in terms of higher strength, reduced thickness, but the formability of such grades of steel was somewhat limited. So consequently, there was only a limited replacement of mild steel in much of the vehicle architecture. This led the steel industry then to focus on the development of a new generation of advanced high-strength steels, which offered significantly higher strength than mild steel, and even many of the high-strength steels available, but with significantly improved formability characteristics, so they could be used in a much higher proportion of the vehicle structure. So the grades of steel that were first developed were dual-phase steels, with tensile strengths varying between 500 to 1,000 megapascals. Since then, there's been an increasing interest in alternative grades of advanced high-strength steels and ultra-high-strength steels, such as trip steels and twip steels, for example, and also in a novel method of the manufacture of steel. It's called the hot forming process. So you take a ferrite perlite grade of steel with 0.03% of boron present, and if you then heat that product in a furnace to temperatures of 850 to 900 degrees centigrade, and then quench that product during the forming stage, during press forming operations, then you can generate a steel with strength levels up to 1550 up to 1900 megapascals. And this has been particularly useful for achieving very high levels of crash resistance during side impact collisions. So this has been the fastest growing grade of steel used in automotive body and white construction over the last 10 to 15 years.
Okay, so there's a lot of stuff there. You've talked about strength, you've talked about boron, which is an element, you've talked about chemistry, you talked about mild steel, and then an upgrade to mild steel, shall we say, which is our high strength steels. So just to give an indication, for the listeners, when Brian talks about tensile strengths, okay, that's how can we say that? How can we sort of break that down into something that's simple? Well, we can say that that's basically how strong the steel is, and a number will be associated with it. So you mentioned the number 900 there, megapascals. Yes. So how does that number compare to, say, a mild steel then, Brian?
Well, typically the tensile strength will be up to, say, 350 megapascals. And the key factor here is that the crash resistance of a vehicle is very much affected by the tensile strength properties of the material. So you need to match the performance of mild steel with a thinner advanced high-strength steel, say, in terms of the crash performance of that section of the vehicle. Boron steels particularly have a key role to play for side impact, and you're looking at alternative grades such as dual-phase steels in front crash zones then in terms of frontal impact.
Okay then, so I guess what makes these steels different then, as you mentioned boron as a chemical, as a chemistry, these steels will all have different chemistries.
That's right, yes.
And that's really one of the key components of what makes them higher strength or lower strength.
And represents a huge challenge for the steel industry. So you're looking to develop steels with much higher tensile properties, whilst at the same time trying to achieve a higher level of formability as possible to give the designers assistance in terms of designing architectures which are attractive to a customer.
All right, well, let's explore that a little bit then, Brian. Let's explore the word architecture, and then we'll go back to actually talking about formability. Yes. And I think that goes hand in hand, doesn't it?
It does indeed.
Yes.
So formability is the ability to form a shape, basically. And the higher the level of formability, the more complex shape you can develop, which, as I mentioned, gives the designers that freedom of design to produce an attractive design of vehicle which will be of interest to a customer, and is a major selling point for customers.
Well, of course, we all want a car shaped nicely, don't we?
That's right, yes.
Okay then, so let's talk about then the main construction method, not construction methods, the architectures. And you mentioned a term body and white, and then there's the suspension and chassis.
Yes, so there's been a major focus on body and white, and that's been the key focus of the steel industry, with less emphasis on chassis and suspension on wheels, for example. So for chassis and suspension, high-strength steels have been the predominant grade of steel used in chassis and suspension applications for many years, where fatigue resistance is critically important. In increasing the strength of a steel to achieve higher levels of crash performance, then higher strength steels are very beneficial. But for chassis and suspension, fatigue resistance is a key attribute which is required to achieve the performance required when travelling on the road. So basically, fatigue resistance is less dependent on the strength of the steel.
Okay. Whoa, we've talked about fatigue resistance now, and another property. Okay, so let's break this down then, Brian. So we've got steels which are used for chassis,
Yes.
which traditionally then have higher strengths
Yes.
and higher fatigue resistance.
Yes.
And then we have the second, or I say the second bit of our architecture, which is our body in white.
Yes.
Which is what part of the vehicle?
Well, that's the whole vehicle essentially. That the front section, the rear section, and the body of the vehicle where the passengers sit. So that's the main thing, and those, of course, lie on top of the chassis and suspension.
Okay. Okay.
So the focus of our discussion today is very much on the body in white of the vehicle, where there is increasing competition from alternative materials such as aluminium. So the steel industry are striving to develop higher strength products to achieve mass reduction, together with looking at advanced engineering solutions such as the use of tailor welded blanks, hydroforming, and other means of achieving an effective weight reduction whilst achieving the same performance.
So a weight reduction then, going back to what you said earlier, that really can only come then from actually making materials thinner.
Yes.
And if you make materials thinner, then obviously they've got less resistance to crash, so we say. They're not going to be as strong.
Unless you increase the strength.
Unless we increase the strength
significantly, yes.
So now we're talking about a range of steels, which is not mild steel. It's an advanced section of steels which need to be produced for the automotive industry.
Yeah. For example, in the future steel vehicle, which is a project which was funded by a group of roughly 20 major steel companies worldwide, the future use of steel in a battery vehicle were analysed, and they came up with an eventual sort of list of products which they felt would be the key products used in a battery vehicle construction. So in this future steel vehicle project for a battery electric vehicle, the amount of mild steel dropped significantly down to 2.6%. High strength low alloy steels of 450 megapascals yield stress. Bake hardening steels with strengths of 340 to 400 megapascals for outer panels of the vehicle accounted for 32.7% of the vehicle architecture. The remaining products used were a combination of hot-formed boron steels, as I mentioned earlier, 11% of such products with a tensile strength of 1500 megapascals.
Well, that's high.
Yes, together with dual phase steels of tensile strength from 500 to 1000 megapascals, trip steels, which contain typically 15% manganese, and also a limited amount of complex phase steels as well. So by doing that, then this is felt to be the optimized use of steel products for the future.
And how does that compare to what we have now then, Brian?
Well, if you look at a typical vehicle architecture in 2007 from the American example, then we're looking at mild and medium high-strength steels of 62.4%, high-strength steels 24%, and then between a combination of advanced high-strength steels and ultra-high-strength steels, they accounted for 13.5% of the vehicle's body in white. By 2015, the situation has changed to some degree, so we see that the mild and medium strength steels are dropped to 52%, and then high-strength steels down from 24 to 18%, and we see a greater use of advanced high-strength steels and ultra-high-strength steels up to 30%. The prediction then for 2025 was that mild steel would then drop to 35 to 40%, high-strength steels 10%, and then the combination of advanced high-strength steels and ultra-high-strength steels would increase to about 50% in total.
So
we see this progressive shift, if you like, from mild steel to the use of high-strength steels, which decrease in proportion to the total use of steels on the vehicle. So we're seeing a drop from 24% to 10% over that 18-month timescale, and an increasing use of advanced high-strength steels and ultra-high-strength steels from 13.5% up to 50% of a typical vehicle architecture. And then, as I mentioned earlier, the future steel vehicle, for a battery electric vehicle, we see a significant further transformation in the use of products that are appropriate for such vehicles in the future.
Okay then, Brian, thank you for that comparison. So I got 2 questions for you. Can you give me a very brief overview, of mild steel? Talk to me about the chemistry in it. Talk to me about what's in it. What makes a mild steel a mild steel?
Well, mild steel is typically 0.03 to 0.04% carbon after the Bosch steelmaking process. Other higher strength levels can be achieved by the additions of carbon in particular, because this is the major element which affects the strength of the steel. You've then got manganese, which is the second primary element that's present in a mild steel product, and you're talking about 15 up to 30%, say, point. Yeah. 0.3 to 0.6% manganese then as the other product that would be the main composition elements, if you like, in your steel product.
Okay, and then there's other things.
And there's other things
like phosphorus and sulfur and these kind of things.
Sulfur tends to be bad news in that it leads to embrittlement in steel. So there's always been a strong focus in blast furnace basic oxygen steelmaking, for example, in reducing the sulfur levels to as low as possible. So prior to the Bosch steelmaking process, there's a desulfurization process to extract as much sulfur out of that product because of the negative effect it has on steel properties. Phosphorus, again, it can have very deleterious effects on embrittlement, for example, when you spot weld a steel together, where spot welding is the primary method of the production of the body in white, where typically there's 4,000 to 5,000 spot welds in your average vehicle structure.
See, it all comes back to the things in the manufacturing process and things like that.
That's it, yes. So formability and welding are key attributes that are necessary to produce a grade of steel that's appropriate for body in white construction.
Okay then, Brian, so that's a brief description of mild steel. Now then, how does that compare to these high strength steels you're talking about? I'm guessing there's going to be something different in the chemistry here, am I right?
Yes, you're talking about, well, there are 3 various grades of high strength steels that are available. You've got niobium high strength steels, titanium and vanadium high strength steels. The preferred product in the UK is niobium high strength steels. So that's a precipitation strengthening element in sheet steel products. And typically the levels would be down to 0.1%, say at the most.
So not much.
So it's not much. Titanium levels tend to be about 2 or 3 times higher. So niobium tends to be preferred because obviously it's going to be cheaper with a niobium steel than a titanium strengthened steel, because you don't need so much of the niobium.
No, okay, well that's a good comparison. We've got mild steel, which has got the main components of carbon, a bit of manganese, silicon.
Yeah.
Then we've got our high strength steels, which have a few more elements put in the mix, like such as our titanium and our niobium.
Yes.
Increasing the strength, increasing the price,
but reducing the formability compared to a typical low carbon mild steel product.
Okay, so what then? So you mentioned earlier that there's still we're not completely reducing the amount of mild steel in our electric vehicles or vehicles into the future. What would you typically use a mild steel for in construction of a car?
For areas of the vehicle, the limited areas where you need particularly advanced formability characteristics, a particularly complex shape. There has been, however, a focus on replacing mild steel in outer panels, for example, by using bake hardening steels.
Bake hardening steels.
So with the outer panels of a vehicle, one of the major concerns is dent resistance. So dent resistance is critically dependent on the yield strength of a material. So mild steel will typically have a certain level of dent resistance, but it's inadequate in situations where you reduce the thickness of the outer panel. So if you want mass reduction for outer panels, then alternative grades of steel are found increasing in attention. So bake hardening steels are steels which have a high level of formability during the forming operation, but then as a consequence of paint stoving, where the temperature of the vehicle goes to a temperature of the vehicle in the paint stoving operation increases up to 180 to 300 degrees centigrade, the carbon and nitrogen, the nitrogen that's present in the steel, precipitates out, which significantly increases the yield strength of the product.
Oh, this sounds exciting. So the yield strength then, let's try and clear that up first for people. The yield strength, you basically can say that's the amount of strength, that's the amount of that's the strength you need to put on, or the force, should we say, to put onto the product to actually get it to deform into the shape we want.
That's right.
And there's a differentiation actually between the yield strength and the tensile strength you were talking about, but we're not going to go into that, okay?
Yes.
But let's just say, so to sum that up, then we've got a situation where a bake harness steel is fantastic because we can use it to form complex shapes like a door panel, like you say.
Yes.
And then we can do that in the manufacturing process, but then we can actually increase the strength of it afterwards by doing the paint stoving.
From the paint stoving operation. So a car, after it's been assembled, is processed through a furnace to cure the paint at temperatures of 180 to 300 degrees centigrade, and with a bake hardening steel, you get a significant amount of precipitation of carbon and nitrogen, which significantly increases the yield strength of the material from a typical mild steel with a yield stress of, say, 180 megapascals up to 300 and even up to 350, maybe in the future 400 megapascals, as a consequence of that precipitation of carbon and nitrogen.
And that's great. So if somebody then flicks a stone at your car or kicks the door,
yes,
then they won't dent. People don't like dents in their cars, do they?
That's right.
I've got enough in mine. I've become peaceful with dents. Have you, Brian?
Yes, I have. And the consequence of and the advantage of this, of course, as I mentioned, is if you're increasing the yield strength of the material, you can reduce the thickness of the steel, which helps in terms of reducing the mass of the vehicle.
All right. Brilliant.
So if you're then looking at the use of advanced high-strength steels, then dual-phase steels, for example, consist of a combination of ferrite and martensite.
Oh, ferrite and martensite. Now, these are grain structures, okay?
That's right. Yes.
There's certain things that make up the shall we say, the profile of the properties of any materials, really, any metallic materials at least. And these are one thing we talked about already, which is the chemistry, and then the other thing is the grain structure. Okay, now we're not going to talk about grain structure here, but just know that there's such a thing called ferrite. Okay, which is
a soft formable material, and martensite, which is a hard product, which limits formability very significantly.
Yeah.
So a dual phase steel will incorporate a high level of ferrite, say, if you're developing, say, a DP600 grade of steel, that's a dual phase steel with a strength of 600 megapascals plus and a small amount of martensite. So the ferrite gives you the formability, and the martensite gives you this resistance to formability, if you like, which increases the strength of the steel. So if you've got a DP600, you typically have 10 to, say, 20% martensite. For a DP1000, you'll have, say, 80% martensite and 20% ferrite. So you have a limited amount of formability, but as you're increasing the strength of the steel and increasing the proportion of martensite that's present, you're progressively reducing the formability of the product. So it's horses for courses.
Yeah,
if you want a high level of formability, then you'd use a DP600 grade of steel, which would have a better performance than, say, a high-strength low-alloy steel with a yield stress of 450 megapascals. So you're tying your sort of application to the ability to form the part, whilst offering the benefit of an advanced high-strength steel, then in giving you better crash resistance, say. than a high-strength steel or a mild steel product.
Okay, yeah. So it sounds like there's just this natural sort of competition between high formability and high strength.
That's right. Yes.
Somewhere you have to get it somewhere on that scale, depending on your application.
Yeah. And there's an increasing focus in the future on the third generation of advanced high-strength steels, ultra-high-strength steels, where you're looking at the use of microstructures, which consist of a combination of ferrite, martensite, and austenite, where you process a dual phase steel to a further step of tempering to introduce a certain proportion of austenite into the microstructure, where austenite has particularly high levels of formability. So that's much of the focus in the steel industry today in meeting the challenges of higher formability whilst matching the very high strength levels that are possible, say, on a dual phase steel product.
I'm guessing then, Brian, that our martensite steels, as we call them now, are they for like the structural components?
Yeah, so for crash zones, for example,
okay,
on the vehicle, so your front longitudinals and other parts of the vehicle where crash has a role to play.
Yeah, you certainly wouldn't want to be using martensitic steels for formable panels, shall we say.
They're called dual phase rather than martensitic.
Oh,
There's
sorry,
another
Brian.
grade of steel called martensitic steels, which have got high levels of strength but negligible formability, shall we say.
Okay. Well, you know what? I think we've covered them with complexity. I mean, I don't blame any of you if you've not been able to follow all that, but I think what we wanted to highlight there is steel is not just steel.
Yeah, not just one grade
you
of
look,
material.
You look at a car and you think, oh, it's a nice car, it's made of steel. Well, and everyone focuses on the batteries and the looks and all that and the range, but there's a lot of work gone into the on the microstructural level.
Yes.
To the selection of materials that are used in these cars. So okay, so I think we've covered that, Brian. I guess what I want to go on to now is that all of these steels have to be made somewhere, don't they?
Yes.
And how do we go about doing that? Because it's as complex as anything, really, isn't it?
That's right. So,
okay. Well, thank you for listening to the first episode, if you made it to the end. And if you did, then you'll know that what I'm going to tell you now, that the title of our next episode is Understanding Steel Grades and Traditional Steelmaking Processes.